folks, we're going to do the last practice problem for this chapter, practice problem number 4. You can get the printout of this. You can see the link in the description or get it from the notes page of our website. As you take a look at this problem, what you're seeing is you're seeing this metal boom. That's the moving at an angle here, or not moving actually, just sitting there at an angle of 30 degrees to the wall. All right, so that angle there is 30 degrees. We're told that it's being held up by a tension. All right, so it's attached to the wall with a cable or a wire, and that wire makes a 90-degree angle with the metal boom. All right, some other stuff that we know. As we've worked at this, like I said, I hope you recognize this kind of like some of the problems that we've been doing in class already, similar to the light pole one, similar to the bear on a platform one, where you've got a net torque, right, of 0, meaning that it's in rotational equilibrium. When we do these types of problems, you have to choose a pivot point. We choose that conveniently, and what I mean by that is that we choose it at a point that is usually at a location where some forces are that we don't know. Now, in this case, the wall is producing or has a force acting on the boom. We don't know what those forces are. And to be honest with you, in the problem here, we really don't care what they are. We're not asked for them. So we're going to put our pivot point there. So when we're doing the net torque, which remember is force times radius times the sine of the angle, the radius is 0, and therefore our torque will cancel out for that force anyway, so it doesn't really matter what that force is. All right, so if we continue sort of filling in some information, it's asking for the mass of the boom. All right, now when we're doing the mass, if you remember again from stuff that we've done in class, the mass we're going to assume is located, because it's not, we're assuming again this is a uniform metal boom, which means that the entire mass can be assumed to act, or it does act, as if the entire mass is located in the exact center. Right? So the force would be that weight force, or the mass of the boom, times gravity. Right? The gravitational force acting on it. And that means that the distance from that is exactly half, right? We're not given an overall distance for this thing. We're just told that, okay, we've got this boom, it has a certain distance. We are told that the tension is 3/4 of the distance, and now we just said, okay, well, that weight force, that gravitational force, is located halfway. So which is a little different. We're not used to that. So what we have to do is we have to put it all in terms that we're, I guess, comfortable with, at least, or make up our variables. Since this is going to be a net torque problem, we generally talk about radius with force times radius times the sine of the angle. So what I'm going to do is I'm going to say, okay, this entire boom from end to end, right, is going to have a length r. In other words, if I was looking, if I had some force on the end of the boom, which I don't in this case, that radius would be r. And then based on the information that I have, the distance from the pivot point to where the tension is attached, right, we're told is 3/4 of the way. So that means that's going to be 3/4 r. And then the distance between the pivot point and where my center of mass is for the metal boom, again, since we're assuming it's uniform, is going to have a distance of 1/2 r. So I don't have the numbers exactly, but I have relationships between the numbers, which will help me as we go through this problem. So we're going to take a look at, again, then this net torque equation like we normally do. And again, remember that is the net torque is the sum of all torques, and torque in general, the generic equation, is force times radius times the sine of the angle between. All right, so we take a look. Again, we have our pivot point located where it hits the wall, and then we have the first, if I start at that pivot point and I start going up the metal boom, I run into my first force, so to speak, and that's the gravitational force of the boom itself. That I know has a magnitude of, right, the mass of the boom, which is what I'm looking for, times g, right? But now I have to, that's the force, right? The radius is 1/2 r. All right, then it's times the sine of the angle. Now, if we look at this, we do a little bit of geometry. We've got parallel lines. The wall is parallel with the force vector here, so I can do a little geometry, the alternate interior angles, and I know that that angle there ends up being 30 degrees for me. So that's sine 30. Now, I look at that and I'm like, okay, but one last thing that we have to watch out for is the direction. Remember our convention. If it's going in the clockwise direction, that ends up being a negative torque. If it's going in the clockwise direction, counterclockwise direction, it's going to be a positive torque. Since this is pulling it down, right, my pivot point's here, it's pulling it down, that's going to cause a torque in the clockwise direction like that, right? That's going to cause it to be negative. So I need to make sure that I put a negative sign there indicating that that's okay, that's a clockwise torque, a negative torque. Then I continue moving out my metal boom. I get to the next force that's supplied by the tension force, right? That's going to cause a rotation in this direction, right? Which is going to be a counterclockwise torque. Counterclockwise being a positive torque, so I'm going to put plus. Then I have my force, which is T, or in this case, I guess I can just substitute that in since I already know the number for it. That's going to be 720, right, times my radius, which is 3/4 r, right, times the sine of 90 degrees, since it's a 90-degree angle. Now remember, we've done this quite often, right? The sine of 90 is just 1, so I really don't even have to put that in there. If you're more comfortable leaving it out, we understand that that is just 1. All right, so if I start working with some numbers here, right, I notice first of all, right, that I've got an r in each one of my terms here. Right, I've got an r in that term, I got an r in that term, so that conveniently I can divide by both terms by r. That r is going to cancel out for me, right, which leaves me with, right, negative mass of the boom times 9.8 times 0.5, right, and if you do the sine of 30 degrees, that is also 0.5, plus 3/4 times 720 is 540. Right, and that leaves out there. I've got all that information left. So now that's equal to 0. I can combine the 9.8, the 0.5, and the 0.5 again. So that's really 1/4 of 9.8. I'm going to bring it over to this side. So that's going to be 2.45 times the mass of the boom is equal to 540. And very easily I can just plug that in my calculator and I get the mass of the boom is 220.4 kilograms. So what started out to look like it was going to be kind of an issue because we don't have the actual radius, the radius actually cancels out in the end, so I really didn't need that to begin with. So ended up being easier than what you might have originally thought. So that's the last practice problem for this chapter. We're looking at the test coming up pretty soon, so good luck on that.